In prior videos, I went through the process of solving for the eigenstates and the eigenvalues, or the energies, of the states of the infinite square wall. So I now want to summarize this a little bit, talk about visualizations, way to interpret, etc. So first, this is what our energy eigenfunction looks like in the position basis. So it's a function of x. And note that this is for this geometry. So to get to this point, we've inherently said that one of the walls of our infinite or rigid well is at x equals 0, the other is at x equals L. The reason that I keep stressing that is that sometimes you'll see this written from negative a to positive a, negative a over 2, positive a over 2. If you change these positions, this will change. So that also means that as you look at one quantum textbook to another quantum textbook, this will also change. So please note this is specifically for that geometry. This term out front, this came from normalization. And remember that we get the normalization by integrating the complex conjugate of the function times itself from negative infinity to infinity. And in this case, when we've written it this way, what's implied here that this is the case for x is between 0 and L. And outside of that, we say that our wave function is 0. So if you take this function and you integrate it from 0 to L, again, this times its complex conjugate, you expect that to be 1. And that's going to be true regardless of what value of n is here. Now this is written in a slightly different format than I've shown in previous videos. So previous videos I was working forwards from the energy eigenvalue equation in the differential form. And at one point there's like a square root of a bunch of stuff, and energy was one of the things that appeared in that. Now then we separately used boundary conditions to figure out what energies were actually allowed. And in particular, we used one boundary condition, the one of x equals 0, to say that this has to be sine and can't have a cosine term. So the boundary condition at x equals L is getting us to this. So once we actually take this, plug it back in for E when I had it in the other form, it simplifies down to be this. So again, it looks a little bit different from prior videos. The book goes through some of these details, but this should check out. So I wanted to discuss a few things in this video. So one is that, again, this is specific to this geometry. So if we change and have a specific value of L, like 2 nanometers, then we can in fact just literally plug those distances in. Great. This m here is going to be the mass of the particle trapped in the well. Probably an electron, could be a proton, could be an alpha particle or a muon or something. So that needs to be the mass of the particle trapped in the well. This is important. This is the first time this has really come up. It might seem like we're just doing math here, but again, there's a physical reason for that. And the model that we see, like when I sketch these wave functions, they kind of look like a standing wave, so you might even forget that we're doing quantum mechanics. But fundamentally, this would be a particle trapped in the well. And this wave function is related to the probability of finding that particle different places. So that mass has to be for the particle in the well. Okay, 2, you know, pi, you know, h bar, you know. So then n. N is, again, our key quantum number here. And n is going to be an integer, and it's positive. 0 is kind of meaningless because that gives you 0 energy, and that's just not a thing. So integer n, and then this relates to that. So before, I was writing this as phi sub ei, but now notice we're just saying sub n, that our energy is described by one quantum number. Later, we're actually going to get to some other quantum mechanics problems where you have more than one quantum number. But right now, we only have one quantum number, so we index that with n, and that's this. It's very important. So notice that energy here depends on n squared. And there's something interesting here that we often represent visually about this. So let's say I have a certain state, and I want to start kind of visually representing my energy levels. And I'll grab a second color flat. So we frequently start drawing this energy bar, and it will make a little more sense to do that when we have more complicated potentials. But we kind of say, okay, what is this? This is E1. And that would be proportional. We have this constant here to 1 squared. Cool. Then we have E2. Notice that that would be as 4. So that isn't just kind of double the height. And the problem is that proportionally, how high can I go? So I'll put it here. This would be E2. But then once I get to n squared, when n is 3, that's 9, so that's like way off the screen, right? So notice that the spacing we get, and I'll just redo it here. So if this is E1, where v equals 0 is right below it, then we have E2 is a certain spacing, right? So this delta from 1 to 4 is 3. From 4 to 9 is 5. From 9 to 16 is 7. So the spacing between these keeps getting bigger and bigger and bigger. So they're not evenly spaced. You should just, draw them as accurately as possible. So that first energy state, well, this is going to be like that. So you don't actually have a full sinusoidal function, and if we think about it, that's 1 pi x over L, and so that's really, when we get here, sine of pi, not sine of 2 pi. The next one goes up, down, up. And again, I've gone off the screen for the next one, so I'll jump down here, up, down. Pretend that's symmetric. It's really hard to draw these well. One of the things I like doing is actually kind of sketching out my points ahead of time so I can do a slightly better job. Cool. So now something to note is that, again, this is representing the probability distribution. So for this state, we actually would say that there's 0 probability of finding it in the middle. So we can kind of think of using this as my phi equals 0 axis for the phi 2, and so this would be positive phi, this would be negative phi. So when we're drawing this, we're kind of drawing these energy lines, but then we're drawing the wave function on top of that to kind of show it. So this is a common way of visualizing these, and it's just helpful to get the details right. So I hope that that's helped a little bit. We'll then do some probability calculations, but again, this is kind of pulling all the pieces together before we jump back into the math.